So as we saw in the previous videos, finding the flux, whether it's something parametrized nicely or something that's a little bit more complicated, can still be a little complex, especially if you have a sphere or if you have a cylinder. You can see that at least the cross product can be a little hard. So luckily for us, we have the divergence theorem, and then what the divergence theorem says is that if you have a closed surface, then you can just take the triple integral of the divergence of the force field. So what we're going to do here is we're going to find the flux over a closed surface bounded by the cylinder y squared plus z squared equals 1. And it has planes x equals -1 and x equals 2. So it's you kind of have a cap on this cylinder over this particular force field. So luckily for us, if you see the word closed surface or something where it indicates that your surface is closed and bounded, then in that case, you can use the divergence theorem. And remember that the divergence theorem says that if you want to find the flux over a surface integral, f dot n ds, this is just going to be equal to the triple integral over the region E of the divergence of the force field. So luckily for us, this is satisfied. So let's go ahead and find the divergence. So divergence of f. So the divergence of f will just be the partial p over the partial x plus the partial q over the partial y plus the partial r over the partial z. So we got all these partial derivatives. So looking at my force field, you can kind of be able to see what each partial derivative with every single respect will be. So partial p over partial x, you can see that guy's just going to give me 3y squared. For q, partial q over partial y, there's no y there, so that guy's going to go to 0. And then partial r over partial z, that's going to give me 3z squared. So this guy is going to be my divergence. And it's what I'm going to plug into my triple integral. So my flux, the flux is going to be equal to the triple integral of the divergence 3y squared plus 3z squared dv over the region E. Now, what exactly is E? All right, so let's draw it. So to figure out what the region E should be, you got your x, you have your y, and you have your z. You have your cylinders. They are in the negative at -1. You're at +2. And you have these circles, okay? And notice that it's oriented on the x-axis. So you got this circle, got this other circle, okay? And you got the cylinder. And these cylinders have planes in them. So actually, this is a cap. Okay, so it's closed here. This guy is also closed in here. So it's an entire closed cylinder. Okay, so there's actually both the top and the bottom. So imagine like it's a soda can, cylindrical soda can, and it's not opened. So now what we got to do is we want to take the triple integral of this, and that will give us a flux. So we got rid of the force field. We don't have to worry about that. And now all we have to do is worry about this triple integral. Now notice that because everything is oriented now towards the x-axis, now your y is still going to be r sine theta, but now your z is going to be equal to r cosine theta. So they kind of swap. So now all we got to think about is what exactly is going to be all of these triple integrals. Now the first integral is going to be with respect to z if it was oriented on the z direction, but now it's on the x-axis. So now the first one's going to be whatever dx was. Okay, so x in this case, notice that it's just the planes from -1 all the way to 2. So that one was pretty easy, 1 to 2. Now, if I want to convert to polar, because it will be nice, I have to have dr d theta. And now I'm going to have an extra r. Okay, now in my integrand, you can see that this is going to be pretty easy because y squared and z squared in this case will give me r squared. And that's just because of the Pythagorean identity. Okay, now what would be my radius in this case? Well, my radius in this case would just be whatever my cylinder is. And you can see that my radius at every single point of this particular solid is just going to be 1. Because my radius is just 1 from the beginning. So this would be from 0 to 1. And my theta value obviously would be from 0 to 2 pi. So all we really have to do is just evaluate this triple integral. So this will be 3r cubed dx dr d theta. So 0 to 2 pi. And notice that I can actually break it up. This one to be in terms of theta. This one to be in terms of r. And this guy to be in terms of x. Okay. So now all I really have to do is just plug everything in there. So the first guy is going to give me just 2 pi. The other guy is just going to give me 3/4 r to the 4th from 0 to 1. And the other one is just going to give me x squared. Oh, there should not be an x in there. It should just be a 1. So you're just going to get x from -1 to 2. Okay. And when you put all that together, you're going to get 9 pi over 2 as my total flux. Okay, which is a lot easier than trying to do a cross product, because if you were to try to parametrize everything, and you would have to do it for every single thing, for the cylinder in the inside, and then for the 2 planes on the outside. So this thing is composed of 3 different things, x equals -1, x equals 2, and the cylinder. And if you wanted to do it the long way, it would have been really, really hard to do. Okay, especially with this vector field when you have all these cubes, because converting it to polar will not be nice. So having the divergence theorem handy is going to be really, really helpful. And sometimes problems will not tell you to use the divergence theorem. Sometimes they will. But if you can see that they're going to be closed surfaces, you can easily find the flux very, very nicely.